Okay, in this lecture, we're going to learn about Gibbs Free Energy. Let's start first by reviewing what we learned in previous lectures on entropy and the second law of thermodynamics. We learned entropy is this disorder, statistical entity that somehow drives what we're likely to see in processes, in chemical reactions, what is going to be spontaneous. The second law of thermodynamics actually tells us that the entropy of the universe always increases for any spontaneous process. So that's sort of summarized down here at the bottom. The change in entropy S that's taking place in the universe is greater than zero for anything that spontaneously happens in the universe, that is, what we observe happening. Now, we know the universe is composed of the system and the surroundings, so we can write this another way by saying that delta S universe is really the delta S of the system. How is the system entropy changing? Maybe that's a beaker of water, a chemical reaction, could be anything. But the universe consists of that system we're interested in and everything else in the universe, which is the surroundings. So we can still have this greater than zero, that if we keep track of all of the system entropy and all of the surroundings entropy, those two added together must be greater than zero. So we can have, our beaker decreasing in entropy as long as the increase in entropy in the surroundings more than makes up for that decrease in entropy, such that those two things combined are greater than zero. So we see some things become more ordered or less disordered around us sometimes, but that's just what's happening in the system. The net increase in disorder in the whole universe is still maintained. Now, in chemistry, this equation, while useful, is a bit problematic because we can't keep track of all the atoms and molecules in the surroundings, that is, the whole universe. So what would be really nice is if we can use this law and recast it just in terms of what's happening in the system. And we'll see by doing that, we derive a quantity known as Gibbs free energy. So here's this first equation that was written on the previous slide, which is just the second law of thermodynamics. Now, we can replace some terms here. We have another equation for delta S, which is Q over T. If this is the system, then it's heat that's going into the system or coming out of the system. And we know from the surroundings perspective, this will be true. Delta S surroundings is just the negative of delta S system based on that heat. So this is to say, if I have heat flowing into a system, it's coming from the surroundings. So Q surroundings is always the opposite of Q of the system, because if heat is flowing into the system, it came from the surroundings. If heat is flowing out of the system, it's going to the surroundings. So those two things are equally true. So my equation for delta S surroundings is Q surroundings over T, or written another way, negative Q system over T. So we can replace that delta S surroundings with negative Q system over T. And we can make one other substitution, which is that our heat flow at constant pressure is really enthalpy. That's how we've derived or defined enthalpy in chemistry. And so we can place that Q system with our delta H of our chemical reaction, if we're interested in the system being the chemical reaction. And so we can replace all of this delta S surroundings with negative delta H over T, which is what we've done here. So now we have this equation. And what's beautiful about this equation is we don't have to keep track of everything going on in the universe. We just need to know the system's entropy, the system's enthalpy, and the temperature of our system. We're going to do some rearrangement here by multiplying both sides by negative T. So we get a negative T multiplied here, a negative T multiplied here, and a negative T multiplied here, which will make this positive. And the T will drop out here. So now we have all of this. The last thing we're going to do is slightly rearrange and just flip the positions of this and this. And that gets us this final equation here. And this is the real powerful part of the equation. It's still the second law of thermodynamics. We've just made some substitutions to recast that second law of thermodynamics with regard to system. And so this combination of enthalpy of the system, temperature, and entropy of the system, or change in entropy and change in enthalpy, I should say, that combination of terms is always going to be less than 0 for any spontaneous process. In other words, reactants will turn into products spontaneously if the delta H of that reaction, the delta S reaction, and the temperature all sum up to give you a number that's less than 0. Now, we sort of give a term to this negative delta S universe that all of this equation is equal to, and we are just going to call that delta G instead, where delta G is this delta H minus T delta S. And this is just simplifying things because now we're going to speak in terms of Gibbs free energy, and we're going to tabulate values for atoms and molecules, and we're going to be able to, for any reaction, just calculate what is the delta G of that reaction. Is it less than 0? Okay, reactants spontaneously turn into products. It's that simple. And you can get delta G by looking up values in a table, by combining measurements of delta H and delta S and T according to this equation. But it's really important to be able to then look at a system energy plot. And if this axis is an axis of Gibbs free energy, and how Gibbs free energy is changing, maybe reactants are over here, maybe products are over here. The reactants will spontaneously move to products if they can lower their Gibbs free energy. So species are always going to move to lower the Gibbs free energy. So if you start off with just reactants, placing a ball here is going to roll down the hill. The reactants are going to move towards products. If this is a graph of how their Gibbs free energy changes as reactants turn into products. But they're not going to roll all the way to products. They're going to settle out right here at the bottom. And so the bottom of this plot, where the ball will settle out, that is our equilibrium. So if delta G is negative, then the process will be spontaneous. So if I'm starting with reactants and the ball is starting uphill, up here, is it going to move to the right? Is that going to be spontaneous? Yes, because the Gibbs free energy is getting lower as I walk down this hill. Okay, if I'm down here and at equilibrium, is it going to be spontaneous to go up towards reactants? No, because that will be a delta G, a change in energy that is positive. Change in Gibbs free energy that is positive, so that's non-spontaneous. And if I'm at the bottom of this hill, I'm going to stay there. I'm at equilibrium. I can't lower my Gibbs free energy anymore. So if delta G is positive, the reaction as written is spontaneous in the reverse direction. So said another way, if I'm down here and I want to walk up to reactants, that is non-spontaneous, which means the reverse process, reactants going down to equilibrium, is spontaneous. Okay, so we can calculate that delta G from a tabulated value of delta H, from a temperature, and from a tabulated delta S like this. And then we can compare, is that greater than 0, less than 0, equal to 0? What does that mean about spontaneity? But we can also directly calculate it from this equation, just like we calculate enthalpy and entropy. It's still products minus reactants, where these N and M terms are still the coefficients in a balanced chemical reaction. So for example, 2H2 plus O2 going to water, 2 waters. If you were looking up the Gibbs energy of water, you would have to multiply it by 2, and you would do products minus reactants, where hydrogen's Gibbs free energy would be multiplied by 2, and oxygen's Gibbs free energy would be multiplied by 1, the coefficient. Okay? So this formula up here is just saying products minus reactants, just like we've always been doing for delta H or delta S. Now, it's good to think about conceptually whether certain things will be spontaneous or not, and how temperature might affect that. So there's sort of 4 different types of combinations of enthalpy, entropy, and temperature that will dictate whether something is spontaneously going to happen or not. So let's think about delta H. That is our enthalpy. When delta H is less than 0, we say that's exothermic. And generally, we sort of associate that with being favorable, right? Sometimes we'll have reaction diagrams plotted as a function of enthalpy. Here's reactants, here's products, it's downhill, exothermic, that's favorable, okay? But we now know that entropy also matters, and it's a combination of H and S that dictates, is that actually going to be spontaneous? But exothermic is favorable for spontaneity. Why? Because the delta H is less than 0, so you're talking about here a negative number for delta H, and you're still subtracting minus T delta S. You want that all to be less than 0 for something to be spontaneous. So having a negative number here for delta H, that is to say, if it's an exothermic reaction, is favorable because that is less than 0. Your temperature here is always going to be positive, since temperature in this formula has to be in Kelvin, and there is no negative Kelvin numbers. Okay, so your temperature is always going to be positive. So it really comes down to this entropy term. If it's exothermic and the entropy is increasing, also favorable, then that combination will always be less than 0 and always be spontaneous. So if I have an exothermic reaction where the entropy is increasing, delta H is negative, delta S is positive, T is always positive, okay, then it's going to be spontaneous at any temperature. Why? Because it's exothermic and it's increasing the entropy. And so it's a negative number minus a positive number. That is always going to be a negative number, always less than 0. So if it's exothermic and increasing entropy, always going to be spontaneous. Now, if it's exothermic and decreasing in entropy, then I have a negative number for entropy, and I'm having a negative number from exothermicity minus a negative number. So this whole term is actually positive, and it'll depend on the size of that positive versus the size of your enthalpy negative, whether or not this thing will be spontaneous or not. So that is this column here. If you're exothermic, negative delta H, and you're decreasing entropy, negative, then it really depends on the temperature. How big is the temperature? So how big is this second term, T delta S, compared to the first term, delta H? And it's a balance between those two things. One of them will win out, and it'll either be positive or negative. Okay? If you're at low temperatures, and so this is a very small temperature here, then this second term is really small, and the first term, which is negative, will dominate such that the whole thing is still negative, delta G less than 0, spontaneous. So at low temperatures, an exothermic reaction that decreases entropy will be spontaneous at low temperatures. At very high temperature, then this second term wins out. And so you're having a negative number from the exothermicity, subtracting from a very large negative number, since the temperature is very large, that'll actually end up in a positive delta G. Okay, and you can just do some quick math. Negative 5, for example, minus negative 100 is positive 95, greater than 0, non-spontaneous. Okay, so that's why I mean a balance between how exothermic and the temperature that leads to the second term being largely negative, if it's a high temperature, or just very, very small negative at low temperature. Okay, and so you can run through each of these arguments. If it's, endothermic, not favorable, and decreasing entropy, not favorable, then it's always non-spontaneous. If it's exothermic, favorable, and it's increasing entropy, favorable, it's always spontaneous. In these other two cases, depends on T. How the balance of those things affect the overall delta G. Here's a quick practice problem. Feel free to pause the video here and try. Okay. For this problem, you're given a delta H, you're given a delta S, and you're asked to calculate delta G. So we're just going to use our delta G is delta H minus T delta S formula. And we're going to plug in each of these numbers. Just be careful here that your delta H, I'm going to turn into joules because my entropy is in joules. So pay attention because usually your delta H and your delta S might have different units, joules versus kilojoules. You want them to be the same when you combine them in this equation. So this negative 92.38 kilojoules will give me negative 92,380 joules. So that's what I'm going to use and plug in here. My delta S, I'm going to plug in negative 198.3. The temperature needs to be in Kelvin, so 298 when I'm calculating at 25 degrees Celsius, and 773.15 when I'm calculating it at 500 degrees Celsius. So plugging all those numbers in, negative 92,380 minus 298.15 Kelvin times negative 198.3 joules per Kelvin should give me an overall answer of negative 33,257 joules. Or equivalently, you could write negative 33.3 kilojoules. Okay, negative spontaneous. So that means this reaction is spontaneous, a negative delta G at 25 degrees Celsius. Now, you can also calculate at 500. The only thing that's going to change there is this temperature is 773.15. Everything else will be the same, and you'll be left with 60.9 kilojoules. Non-spontaneous because that delta G value is greater than 0. The bonus question here at the bottom says, what temperature does the reaction change from spontaneous to non-spontaneous? So when does it change from negative to positive? Delta G will change from negative to positive at 0. When delta G is equal to 0, it's passing from a negative number to a positive number. So it's asking you to calculate the temperature now at which 0 equals negative 92,380 minus T times negative 198.3. I've left off my units here for brevity, but this is what it wants you to do to solve for the bonus. So add 92,000 by both sides, okay, divide by 198.3, you should be left with a temperature in Kelvin of about 446 Kelvin. Now, the last thing to talk about here is that all the delta G's we get from tables, the delta S's, the delta H's, you'll see this degree sign. This degree sign means standard conditions. So the ones you're looking up in tables are based on reactions where the pressure is always 1 atmosphere, and if you have like aqueous solutions, concentrations are always exactly 1 molar, and most of our reactions and chemistries are not going to be at these perfect idealized conditions. But scientists have sort of collected all that data at these standard conditions. If you want to adjust for other pressures or other concentrations, you need to account for that with this Q, where Q is still products over reactants in terms of their concentrations or pressures. So you're going to look up the delta G from the table, but then you're going to adjust it by this R, T, and ln of products over reactants. What are the actual pressures and concentrations, not these idealized one. Okay, just remember that R here is 8.314 joules per mole Kelvin, and your T here has to be in Kelvin. Okay, so you want a delta G in joules to match up with this R, joules per mole Kelvin. So you're going to look up the table from the table and figure out your delta G at standard state. You're going to add to that R times T times the natural log of this ratio of products to reactants at these actual pressures, not some idealized pressure. So that's how you'll solve problems of that type. Now, at these non-idealized pressures and concentrations, you can still have a reaction that reaches equilibrium, which is to say its delta G will eventually get to 0. And so when this real reaction gets to equilibrium, delta G is 0, and instead of using Q, we use K because that's our equilibrium constant, products over reactants. All of this means is you can have a unique rearrangement here at equilibrium to actually define how delta G connects to K, which was our equilibrium constant we've discussed a lot in previous lectures and topics. So this is the real connection. These two equations are the same, just rearranged, solving for delta G versus K. They're the same equation, right? But it shows the relationship between this Gibbs free energy at standard state and what the equilibrium balance will be between products and reactants. So you can always go back and forth between your equilibrium constant for a given reaction and its delta G at standard state. So that summarizes delta G and how we've derived it from the second law, and it being a combination of entropy and enthalpy.